You are incredibly smart. You can type a question into a glass rectangle in your hand and retrieve the sum of human knowledge in seconds. You can buy a plane ticket and fly across an ocean. You can adjust the temperature of your living room with a dial. But now, let's ask an uncomfortable question. If we dropped you in a remote forest tomorrow, with no phone, no map, no matches, and no instructions, how long would you last? Could you find clean water? Could you identify which plants are medicine and which ones will stop your heart in an hour? Could you start a fire without a lighter? Could you build a shelter that survives a storm? Probably not. And that is not an insult. It is just the reality of modern life. We live in a world where we have outsourced almost all of our survival. We look back at cave paintings and stone tools and we think, how primitive, how simple. We treat history like a slow crawl from stupidity to genius. But the science says something very different. Because your ancestors were not stupid. In fact, compared to you and me, they might have been absolute geniuses. To understand how helpless we have become as individuals, we have to look at a famous experiment conducted by a design student named Thomas Thwaites. In 2009, Thwaites decided to do something seemingly simple. He wanted to build a basic, cheap electric toaster from scratch. The kind of toaster you can buy at a local grocery store for about $7. He took a cheap toaster apart and found it consisted of over 400 separate pieces made of various materials: steel, copper, plastic, and mica. So he set to work. To get the iron for the steel frame, he had to travel to an abandoned mine, dig up raw iron ore, and melt it down in a homemade chimney furnace, using a leaf blower to pump in oxygen. To get copper for the wires, he had to find a copper mine, collect raw materials, and attempt to refine them. To get plastic for the casing, he tried to extract oil, but realized that was nearly impossible. So he resorted to melting down plastic trash and trying to reshape it. The project took him 9 months. It involved thousands of miles of travel. It cost him thousands of dollars. And the result? A warped, melted, terrifying-looking appliance that resembled a radioactive cake. When he finally plugged it in, it worked for exactly 5 seconds before the heating element melted itself into a puddle. It took an entire global civilization, millions of hours of accumulated human history, and massive supply chains just to toast a slice of bread. This is the central paradox of modern human life. We are surrounded by godlike technology, but as individuals, we are completely helpless. If you're a software engineer, you know how to write code, but you don't know how to mine the silicon to make the microchip. You don't know how to harvest the rubber to insulate the power cord. You don't know how to generate the electricity that powers your screen. We are hyper-specialized. We know one tiny fraction of a percent of what is required to keep us alive. Now compare that to an ancient human living 40,000 years ago. If that individual did not know how to identify every plant in a 50-mile radius, they died. If they did not know the migration patterns of every animal, they starved. If they did not know the physics of flint knapping, they had no tools. If they did not know the chemistry of wood and fire, they froze. The ancient human was not a specialist. They were the ultimate generalist, and they had the brain to prove it. Let's look at a physical measurement: your skull. Your brain is a massive, power-hungry machine. It weighs about 3 pounds and consumes a fifth of your daily energy, even when you are just sitting on the couch watching a video. We assume this brain is the peak of human evolution, the biggest and most complex it has ever been, except it isn't. When anthropologists measure fossilized skulls from the Ice Age, they find a startling trend. Neanderthal brains were, on average, larger than yours. They had a brain volume of around 1,400 to 1,500 cubic centimeters. Even early Homo sapiens living 30,000 years ago had brains that averaged around 1,500 cubic centimeters. But today, the average human brain volume is around 1,350 cubic centimeters. Over the last 30,000 years, the human brain has actually shrunk by about 10%. Think about that. We have lost a chunk of brain tissue roughly the size of a tennis ball. Why? Some scientists suggest it is a form of self-domestication, just as domesticated dogs have smaller brains than wild wolves because they no longer have to struggle to survive. Humans may have softened their brains as society became safer. But there is another theory, the collective brain theory. We didn't get stupider as individuals. We just stopped needing to store all of our data locally. When humans began living in larger groups, we started dividing labor. We didn't need every single person to be a master tracker, a master botanist, and a master tool maker. We could split up the work. And once we invented writing, we didn't even need to keep the data in our heads anymore. We could save our files to the cloud, which back then was clay tablets, papyrus, and paper. Our brains got smaller because we outsourced our intelligence to the group. But before we did that, back when every single human had to carry their own hard drive, the cognitive demands of daily life were staggering. To survive in the Pleistocene, you had to be a walking encyclopedia of botany, zoology, geology, meteorology, and engineering. And if you think that sounds like an exaggeration, we need to talk about ancient chemistry. We tend to look at Stone Age tools and see, well, just stones. A hand axe, a spear point, a scraper. They look simple, but a stone point is useless unless you can attach it to a wooden shaft. This process is called hafting, and it is one of the most important technological leaps in human history. If you just tie a stone point to a stick with leather cord, the impact of hitting an animal will cause the stone to wobble, loosen, and fly off. You need glue, but you cannot just walk up to a tree and scrape off some sap. Natural pine resin, for example, is extremely sticky, but once it dries, it becomes incredibly brittle. If you hit a mammoth with a spear held together by raw resin, the impact will shatter the glue instantly, and the spearhead will fall off. To solve this, ancient humans, both Homo sapiens and Neanderthals, became chemists. Over 70,000 years ago, early humans began creating compound adhesives. They would gather pine resin and mix it with specific additives. One of the most common additives was red ochre, a natural clay rich in iron oxide. Now, why ochre? Ochre acts as a structural filler. It is made of tiny microscopic plates of minerals. When mixed with the liquid resin, these plates create a composite material, similar to how modern engineers mix fiberglass with resin to make strong car bodies. The ochre stops cracks from spreading through the brittle resin. But they couldn't just throw random amounts of clay and sap together. In modern laboratory recreations, scientists have tested these ancient recipes. They found that if you use too much ochre, the glue becomes dry and crumbly. If you use too little, it remains too soft. The ideal recipe? Roughly 7 parts resin, 3 parts beeswax, and 2 parts ochre. And remember, they had to cook this mixture over an open campfire. If they heated the mixture too much, the resin would burn and lose its adhesive properties. If they didn't heat it enough, the ingredients wouldn't blend. Without thermometers, without measuring scales, and without chemistry sets, they managed to master the precise thermodynamics of polymer engineering. But it gets even more impressive. If we look at Neanderthals in Europe, we find an even older, more complex chemical process, the creation of birch bark tar. Birch tar is the oldest known synthetic material in human history. It has been found on Neanderthal tools dating back more than 200,000 years. Unlike pine resin, which leaks naturally from trees, birch trees do not secrete tar. You cannot scrape it off the bark. The only way to get birch tar is through a process called dry distillation. You have to take rolls of birch bark, place them in an airtight container, bury that container underground, and build a fire on top of it. This creates a high-heat, oxygen-free environment, a reducing atmosphere, where the bark is heated to between 340 and 400 degrees Celsius. Under these exact conditions, the bark undergoes a thermal-chemical transformation, releasing a thick, black, waterproof tar that drips down to the bottom of the container. If oxygen leaks into the chamber, the bark simply catches fire and burns to ash. Think about the sheer cognitive complexity required to invent this. You have to imagine a chemical reaction that is entirely invisible to you because it is happening underground, inside a sealed pit, beneath a roaring fire. You have to control the temperature of a fire you cannot measure, and you have to do this without any metal or ceramic vessels. For years, some modern scientists argued that Neanderthals must have stumbled upon birch tar by accident, perhaps scraping it off rocks after a forest fire. But recent chemical and archaeological analyses have put that theory to rest. The molecular structure of the tar found on ancient tools proves it was distilled in highly controlled, underground, oxygen-poor setups. And in 2026, researchers published a study in PLOS One showing that Neanderthals didn't just use this tar as glue. The study found that experimentally produced birch tar has powerful antibacterial properties, specifically hindering the growth of Staphylococcus bacteria, which is notorious for causing wound infections. Neanderthals were using this synthetic material not just to hold their spears together, but as a pharmaceutical treatment for open wounds. 200,000 years ago, they had mastered pyrotechnology, organic chemistry, and pharmacology, and they did it all in the dirt. Let's move forward in time to a different environment, the open ocean. If we want to see the peak of human spatial intelligence, we have to look at the colonization of the Pacific Ocean by the Polynesians. Between 3,000 and 1,000 years ago, Polynesian voyagers set out from islands in Southeast Asia and colonized almost every habitable island across the vast Pacific, from Hawaii in the north to Easter Island in the east to New Zealand in the southwest. This area, known as the Polynesian Triangle, covers over 10 million square miles of open water. To put that in perspective, the Pacific Ocean is so vast that you could drop the entire landmass of the Earth into it and still have room left over. And the islands they were looking for were tiny specks of rock and sand. Finding Easter Island in the middle of the Pacific is like trying to find a single grain of sand on a football field. The Polynesians did not have compasses. They did not have sextants. They did not have metal instruments. They did not have maps. Yet they sailed wooden double-hulled canoes across thousands of miles of trackless blue, hit their targets, and returned home to tell the tale. How? They used a system of navigation called wayfinding. Wayfinding is not just looking at the stars. It is a massive, real-time data processing system that reads the environment like a living map. A master Polynesian navigator could read the ocean swells. When wind blows across the ocean, it creates waves. But those waves travel thousands of miles even after the wind has died down, creating a steady pattern of swells. When a swell hits an island, it bounces off it, creating a refracted wave pattern that travels backward. A navigator sitting in a canoe could feel the subtle rocking of the boat and detect the interference pattern where two different swells met. By feeling the rhythm of the waves, they could tell if there was an island hidden over the horizon up to 50 miles away. They read the sky. They knew the exact path of hundreds of stars, knowing exactly where they rose and set on the horizon at different times of the year. They read the clouds. They looked for a faint greenish tint on the underside of distant clouds, a reflection of light bouncing off the shallow turquoise water of an island lagoon that was still invisible below the curve of the earth. They read the birds. They watched white terns and noddies. These birds fly out to sea to fish in the morning, but must return to land at night to sleep. By tracking the flight path of a single bird at dusk, a navigator knew exactly which direction land lay. This required a level of focus and memory that is almost unimaginable to a modern person. A navigator had to stay awake for days at a time, keeping a running mental calculation of their speed, direction, drift, and time. If they lost concentration for even an hour, their mental map was wiped clean, and they would be lost in the void. This wasn't a primitive way of traveling. It was a highly sophisticated, multi-generational science that required its practitioners to hold a dynamic, three-dimensional simulation of the Pacific Ocean inside their heads. But you don't need to look at ocean voyagers to see this level of genius. You can find it on the ground, in the simple act of tracking an animal. To a modern city dweller, tracking looks like magic. A tracker looks at a patch of dirt, points, and says, "An injured kudu passed here 3 hours ago." But tracking is not magic. It is the origin of the scientific method. Before we had laboratories, Before we had microscopes, the human mind had to develop the ability to form hypotheses, analyze data, and draw logical conclusions based on indirect evidence. Think about what a track actually is. It is a sign of something that is no longer there. To read a track, a hunter-gatherer must engage in a process called systematic tracking. First, they identify the species. This requires memorizing the exact hoof or paw prints of hundreds of different animals at different ages and in different soil types. But that is just the beginning. A master tracker looks at the depth of the print. Is the heel print deeper than the toe print? That means the animal was running, pushing off with its feet. Is one side of the print shallower? The animal is limping. It has an injury. They look at the soil. If the edges of the footprint are sharp and loose, dirt has not yet blown into the depression, the track is fresh. If the edges are rounded and dry, the track is hours old. They look at the plants around the track. Is a blade of grass bent? Has it started to turn yellow where it was crushed? If the grass is still green, the pressure was applied recently. If it has started to dry out, hours have passed. They look at the droppings. They break open the animal's dung. Is it warm? Is it dry on the outside but moist on the inside? What seeds are in it? This tells them not only when the animal was there, but what it was eating and where it is likely going next to find more of that food. This is forensic science. The tracker takes a series of static, isolated clues in the dirt and reconstructs a dynamic, moving story in their mind. They must project themselves into the mind of the prey. If I am a thirsty wildebeest and the wind is coming from the north and I am limping on my left leg, which path will I take to reach the river? This requires empathy, imagination, and rigorous logical deduction. Some anthropologists argue that this cognitive leap, the ability to look at a mark in the dirt and visualize the animal that made it, is the exact same cognitive software we use to look at letters on a page and visualize the thoughts of a writer. Tracking did not just feed us, it taught us how to think. So, if our ancestors were so brilliant, why did they live in caves and hunt with spears, while we live in cities and launch rockets into space? If we have smaller brains and less individual self-reliance, how did we build the modern world? The answer lies in the difference between individual intelligence and cultural intelligence. As individuals, we are not smarter than our ancestors. In fact, if we could somehow clone an Ice Age baby and raise them in a modern home, they would easily learn to code, drive a car, or perform heart surgery. Physically and mentally, they were just like us, perhaps even slightly more robust. But our power does not come from our individual brains. It comes from our ability to cooperate, share information, and accumulate knowledge over thousands of generations. Joseph Henrich, an evolutionary biologist, refers to this as the collective brain. Imagine two groups of people. Group A consists of 10 brilliant geniuses. Each of them is incredibly smart, but they live in complete isolation. They never speak to one another, and they never pass their knowledge down to their children. Group B consists of 100 average, ordinary people. They are not geniuses, but they are constantly talking, sharing ideas, and teaching their children what they have learned. Over time, Group B will develop far better technology than Group A, because one person in Group B might invent a slightly better way to shape a spear. They teach it to 10 others. One of those 10 figures out a better way to attach a feather to the back of the spear. They teach it to 20 others. Knowledge accumulates. It compounds like interest in a bank account. No single person in Group B has to reinvent the wheel. They just start where the previous generation left off. This is why we have smartphones. No single human alive today knows how to build an iPhone from scratch. The person who designed the glass does not know how to write the operating system. The person who programmed the camera does not know how to mine the lithium for the battery. We are all tiny nodes in a massive global network of shared intelligence, and that is our greatest strength. It has allowed us to eradicate diseases, build civilizations, and peer into the depths of the cosmos. But it has also made us incredibly fragile. We have traded individual resilience for collective power. We have created a world where we are entirely dependent on the survival of the network. If the grid goes down, if the supply chains collapse, if the collective brain experiences a glitch, most of us do not have the skills to survive the month. So, were ancient humans geniuses? By our modern specialized standards, they might not look like it. They didn't know algebra, they didn't know about gravity, and they didn't know how to build a steam engine. But that is because they were working on a different set of problems. They were the pioneers. They had to figure out the basic rules of reality with zero guidance. They had to look at a seed and realize it could grow into a plant. They had to look at a horse and realize they could ride it. They had to look at a heavy rock and realize it could be rolled. Every single piece of technology we take for granted today, from the clothes on your back, to the bread in your kitchen, to the language you are using to understand this video, sits downstream of a breakthrough made by an ancient generalist who had to figure it out in the dark. They were not confused mud goblins wandering through the wilderness. They were hyper-focused, deeply observant, creative problem solvers. They were material scientists who worked with bone and ash. They were master navigators who read the stars and the ocean. They were forensic detectives who read the stories written in the dirt. We are not the geniuses who invented the world. We are just the children playing in the house they built. And perhaps the next time you turn a handle and watch clean, warm water appear, you will think of them, not with pity, but with awe.